I present the film evaporation drum, developed according to the patent RU 2,488,421 C1 concentration of liquid solutions. This is a new type of universal thin film heat exchangers that can be used for distillation and concentration processes of solutions in various industries, for example, for the concentration of liquid radioactive waste or for multi-stage water desalination. Thanks to the technology used for continuous mechanical cleaning of the heating surface from salt deposits, these devices have an unlimited cycle between stops for chemical or mechanical cleaning. The use of film evaporation drums for solutions will allow consumers to solve the problem of scale formation on heat exchange surfaces during evaporation and distillation of solutions. Ensure a high degree of purification of secondary steam from aerosols. Eliminate the need to use chemicals to combat scale. Ensure energy-saving operation and low operating costs. Completely or partially return the solvent to the technological cycle. Achieve a given high level of solution concentration. Technical and technological feasibility of the project. The technology is based on the use of exclusively known and proven physical processes: evaporation of thin films, condensation, heat transfer through the wall, etc., carried out in many types of heat exchange equipment: rotary evaporators, roller dryers, film evaporators, etc. The market will demand equipment with an unlimited cycle of operation between stops for the purpose of cleaning from salt deposits, low operating and energy costs. Potential consumers include a wide range of enterprises from various industries that use evaporation and concentration of solutions prone to scale formation in their technological processes. Atomic industry, processing, concentration of liquid radioactive waste. Non-ferrous metallurgy, evaporation in hydrometallurgical technologies. Chemical and food industry, concentration of solutions of mineral and other salts, as well as alkalis. Pharmaceutical and food industry, production of concentrated liquid extracts of plant materials and regeneration of the extractant. Washing and cleaning, regeneration of process water from washing machines. Galvanic production, galvanic solutions and rinsing waters. Recycling of toxic solutions and industrial wastes, etc. Distillation and concentration of solutions in film evaporation drums. A simple principle, an effective result. Recirculation of thermal energy ensures high efficiency of the process and eliminates the need to use heating steam and a cooling circuit. A drum film evaporator with a self-cleaning system ensures a continuous operating cycle without deteriorating heat transfer parameters. Automatic operating mode with a simple monitoring and control system. Possibility of using an additional secondary steam after treatment system. Multifunctionality of the complex, distillation, extraction, concentration. Low requirements for personnel qualifications. High maintainability. Relatively low cost of devices and their installation. The weight and dimensions of evaporators are convenient for transportation and transport and technological operations. In nuclear energy, dose loads on personnel are sharply reduced due to the absence of the need to clean heat exchange tubes from deposits. Low operating costs. Convenient integration into a continuous technological cycle. The most promising direction for mass production of film evaporation drum, FED, is the production of multi-stage desalination plants with zero liquid discharge. Let us consider in detail the design of a separate module of a 10-stage evaporation plant, which, in regions with maximum insulation, ensures the production of fresh water on average about 10 cubic meters per day, about 1 cubic meter per day for each module. The main structural element is a rotating drum made of thin-walled large-diameter pipe, partially filled with liquid. For the example under consideration, the internal diameter of the thin-walled pipe is 480 mm, the wall thickness is 2.5 mm, and the pipe length is 6 meters. Heat is supplied from the outside of the rotating drum and removed by evaporation of water from the wetted inner surface. If the drum is heated by water steam, then the pressure outside the drum is greater than the pressure in the internal cavity. Therefore, to prevent the body from collapsing, the drum is equipped with external rings located at equal distances along the length of the drum, which imparts rigidity to the structure. In the design under consideration, the inner diameter of the ring is 485 mm, the outer diameter is 504 mm, and the ring width is 8 mm. The smaller the distance between the outer rings of the drum, the more resistant the drum is to external pressure, which can cause it to collapse, and the smaller the thickness of the drum wall can be. When the drum rotates, the outer surfaces of these rings rest on ceramic bearings mounted in paired rings of annular supports, rigidly fixed relative to each other at a distance of 9 mm. Ring supports with an outer diameter of 549 mm and an inner diameter of 506 mm are installed in a cylindrical FED body in the form of a pipe with an inner diameter of 550 and an outer diameter of 554 mm. To increase the space for installing ceramic bearings, the holes for the drum in the support rings are shifted upward by 25 mm. Uniform placement of ring supports along the length of the drum distributes the load, so ceramic bearings operate at loads much lower than designed, which has a beneficial effect on their service life. Another factor that ensures a high bearing life is the material from which the bearings are made. This is ceramic that is highly corrosion resistant and does not require lubrication. Pure water vapor conditions are ideal for the operation of these bearings, ensuring low mechanical losses when the drum rotates. The assembly of a film evaporation drum module with steam heating is quite technologically advanced and does not present any particular difficulties. Depending on the customer's needs, ready-made modules can be installed in a production line either in parallel or in series. When heating steam is supplied to the housing, it must pass freely along its entire length through the ring supports in the channel between the housing and the drum, for which holes are made in the expanded part of the ring supports. At the very bottom of the rings there is a cutout for condensate to drain to the discharge point from the housing. The most important design element of film evaporation drums, which distinguishes them favorably from other evaporators, is a system of continuous mechanical cleaning of the heating surface when concentrating scale-forming solutions. This system is quite simple and in the design under consideration consists of a thin metal strip twisted into a spiral, rolling under the liquid level inside a rotating drum under its own weight. To increase the impact of the screw edges on the heated surface in order to clean the surface, inside the spiral there is a heavy metal rod that rolls along with the spiral. In this case, the inner edges of the spiral also clean the surface of the rod from deposits. The small thickness of the spiral metal tape ensures its elasticity and periodic oscillations of the turns relative to each other, which creates conditions for the detachment of deposits from the surface of the tape itself. In this way, conditions are created to maintain the functionality of the system for mechanical cleaning of the heating surface. The rotation of the belt and the impossibility of its movement in the longitudinal direction due to the limitation by the ends of the drum forces the belt to perform the function of a screw that moves precipitated particles from the bottom of the drum to the discharge side, where the suction section of the tube for periodically removing concentrate from the drum is located. The efficiency of solution evaporation is ensured by the mode of film evaporation from the wetted inner surface of the rotating drum. To do this, a constant liquid level must be maintained at the bottom of the drum. This purpose is served by a float valve, which automatically regulates the flow of the solution supplied for evaporation, for example, seawater. Unlike the flow of liquid constantly entering through the float valve, the concentrate is removed periodically, only when the required salt concentration is reached. When desalinating seawater, the high concentration of salts in the solution removed from the FED creates conditions for the effective removal of small residual water and drying of this concentrate to the state of dry salt. The tightness between the heating steam and the secondary steam generated in the drum is ensured by a mechanical seal made of ceramic rings. A large FED length can cause the body and drum to deflect under its own weight, which will significantly increase mechanical losses during drum rotation and require an increase in torque and, accordingly, drive power. In order to avoid deflection of the FED under its own weight, the body is supported by a rigid structure made of steel beam. Providing a rigid support for the FED housing to prevent housing flexing allows the drum and housing to be extended in length with a corresponding increase in performance. At the same time, the cost of installation will increase much more slowly than its productivity. Secondary steam is removed from the drum through an axial pipe equipped with a hermetically sealed end seal. In the FED design under consideration, drum rotation is ensured by a worm drive. The drum shaft is driven into rotation by a worm wheel, which is coupled with a worm screw. With a vertical arrangement of FED modules, the worm wheels of all drums are driven by a worm screw located on the same shaft, which can rotate from one drive, for example, a gear motor. Clean water from the FED, condensed on the outer surface of the rotating drum, is drained automatically through a thermodynamic condensate drain. Heating of film evaporation drums can be done in different ways. In a solar desalination plant, steam is generated by solar energy, which is concentrated in a parabolic reflector. The internal structure of a rotating drum installed in a parabolic reflector with a single axis of rotation is similar to that already discussed for the evaporator module. Similar reflectors are used in solar power plants to heat circulating molten salt. The outer surface of the rotating drum installed in the reflector should be covered with a light-absorbing coating to increase the efficiency of solar energy use. In calculation estimates, it is accepted that the surface area for reflecting solar rays is 70 square meters, and to ensure the average productivity of a multi-stage desalination plant of 22 cubic meters of fresh water per day, thermal energy is required from 3 reflectors, which can provide the required amount of high-parameter steam. In the presence of high-pressure steam of 550 kilopascals, which is generated in film evaporation drums installed in parabolic solar concentrators, it is possible to ensure a multi-stage evaporation process according to a sequential installation scheme of film evaporation drums. In this case, for the design under consideration, the solar desalination productivity can be increased by 10 times. The table shows the distribution of technological parameters across 10 stages of evaporators. Steam generated in solar concentrators with a pressure of 550 kilopascals and a temperature of 155.5 degrees enters the steam jacket of the lower module drum and generates secondary steam with a pressure of 484 kilopascals and a temperature of 150.6 degrees. This steam enters the heating steam jacket of the second stage and so on along the chain up to the 10th stage. Secondary steam of the last 10th stage with a pressure of 143 kilopascals and a temperature of 110 degrees is sent to the steam air condenser and heats the air, which is used to dry the salt concentrate to the state of dry salt. Of course, the use of solar energy as a heat source for film evaporation drums is only a special case for regions with very high levels of insolation. And for this case, it is most rational to use a multi-stage connection scheme for film evaporation drums. In the absence of high-pressure steam, the optimal technology is mechanical steam recompression, when film evaporation drum modules are connected in parallel. In this case, the steam generated in the modules is sent through a manifold to a compressor, for example a Roots pump, and after increasing the pressure and temperature of the steam in the compressor, the same steam is sent as heating steam from the same film evaporation drum modules, where it condenses on the outer surface of the rotating drums. With this scheme, there is no need for a source of heating steam and a cooling circuit for its condensation. This technology can be used to concentrate liquid radioactive waste for subsequent immobilization, for example, in a cement matrix. More detailed information about this can be obtained from the links. The purpose of this video is to make film evaporation drum technology accessible to a variety of industries. It is expected that this will be an open technology that, in particular, will help solve the problem of lack of fresh water in countries with hot climates and the problem of neutralizing liquid radioactive waste. Patenting should not hinder the widespread adoption of this technology for desalination, distillation, extraction and solution concentration purposes. If you have any technical questions, you can contact us by email uzikov62@mail.ru.